Welcome to the Theory of Computation. This is lecture number 4. Today's lecture is going to be once again about designing Turing machines. In the last lecture, we looked at some examples of very simple Turing machines, and in the end, we looked at a slightly complicated example of a Turing machine. We'll continue with that example today. After that, we would learn how to design Turing machines for some other interesting languages. This would give us some experience in designing Turing machines, and we'll get familiar with most of the tricks of the trade that are used in designing these Turing machines. Remember that to specify a Turing machine, you must specify the 7 things that are required for the definition. Let's go back and look at the problem that we were looking at in the last lecture. We had a language A, which was the set of all strings of the form 0 to the 2 to the n. This means that the language consists of the string 0, 0, 0, 4 zeros, 8 zeros, 16 zeros, 32 zeros, 64 zeros, and so on. Right? So this language consists of all strings which are made entirely out of zeros, and the length of the string has to be some power of 2. What we want to do is to design a Turing machine that accepts precisely this language. In the last lecture, we looked at one such Turing machine. That Turing machine had 7 states, and Q1 was the initial state, QA was the accept, and QR was the reject state. The most important thing about this Turing machine was its transition function, which was given by the following state diagram. Let's have a look at this state diagram in more detail. As you can see, the start state is Q1. The first state is only used to mark the first square of the input. This way we will know where the left end of the tape is. Q1 simply puts a blank in the first square. So if it sees a 0, it converts it into a blank. However, if Q1 doesn't find a 0 there, it simply rejects the input. The second state, Q2, skips over all the symbols that have been crossed out and finds the first 0 that has not been crossed out. If you see from Q2 on input 0, we cross it out and move right. So it crosses off the first 0 that it finds. The state Q3 skips over all the crossed out symbols and waits till it sees a 0. When it sees a 0, it simply moves to the right and goes into the state Q4, which means in the state Q3 we do not cross out a 0 when we see it, we simply move to the state Q4. Q4 is very similar to the state Q3. It skips all the crossed out symbols and waits for a 0. If it sees a 0, it crosses it out and goes back to state Q3. On the other hand, if it doesn't see a 0 and sees a blank, it goes into the reject state. So the input is rejected. As long as there are zeros or crosses, Q3 and Q4 are the states that the machine will alternate between. In Q3, it'll skip the 0 and go to Q4. In Q4, it'll go to state Q3 but cross out the 0, thereby crossing out every alternate zeros. On the other hand, notice that when we are in state Q3, we have seen an even number of zeros. And if we are in the state Q4, we have seen an odd number of zeros, and the number of zeros we have seen is strictly greater than 1. So if we see an odd number of zeros and the input ends, the machine simply goes into the reject state. You will also notice that if the input ends when we are in state Q3, that is, if we see a blank, we start moving to the left. The state Q5 is simply moving the head towards the left till it comes to the leftmost cell of the input tape. So in Q5, we keep moving to the left till we see the blank. Remember, in the state Q1, we had put a blank in the leftmost cell. So you can think of Q5 as a state that rewinds the tape in the sense that it brings the tape head all the way back to the first cell of the Turing machine. And once again, this process starts all over again. What is happening in this Turing machine is the machine goes over the input over and over again and crosses out every alternate zero. it checks whether the number of zeros on the tape was an odd number. If it was, it simply rejects the input. And if all the zeros are crossed out and in the end we are left with just 1 0, then the Turing machine accepts this input. Why would this work? Well, let's think about it. Suppose that I started off with 64 zeros. Then the machine will cross out every alternate zero and there will be 32 zeros left on the input tape with some crosses. The second pass that the machine makes over its tape, it would reduce the number of zeros to 16. And in the next pass, this would be reduced to 8. And in the next pass, it will be reduced to 4. And in the next pass to 2. And finally to 1. And the machine will accept this input. This is how it will accept a string which consists of 64 zeros. On the other hand, let's say we give it 100 zeros, and remember that 100 is not a power of 2, the machine will cross off every other zero and there will be 50 zeros left on the input tape. At this point, the machine will continue. In the next phase, the machine will cross off every other zero and there will be 25 zeros left on the input tape. In the next phase, the machine will try to cross off every other zero. However, it will realize that the number of zeros on the input tape was an odd number which was greater than 1 and therefore reject this input. This was a very simple example of another language for which we were able to design a Turing machine. We have to get familiar with the concept of Turing machine, so let us look at another example. Let us look at this language B, which consists of the set of all strings W followed by a hash sign followed by a W, where W is a string over zeros and ones. So this language actually consists of a string of zeros and ones followed by a hash sign followed by the same string of zeros and ones. We want to design a Turing machine that would accept all the strings in this language and reject all the strings that are not in this language. In order for us to design this Turing machine, we have to first understand this language. We must first be very clear about what are the strings that are in this language and what are the strings that are not in this language. Let us look at some examples of strings that are in the language. Some strings that are in the language are 0110, hash sign 0110. As you can see, this string consists of a segment which is a string over 0 ones, and then I have the hash sign followed by the same string. Similarly, 0 hash sign 0 is also in the language. Similarly, just the hash sign is in the language. In this case, the string W happens to be the empty string. So we can think of the hash sign as the empty string followed by the hash sign followed by the empty string. Another string that is in the language is 000 hash sign 000. As you can see, this is also a string of the form W hash sign W. We should also understand what are the strings that are not in the language. So these would be all the strings which do not have the form W hash sign W. Some examples of these strings are 1010 hash sign 1100. As you can see, in this case, the two strings on the opposite side of the hash sign are not equal. Therefore, this string is not in the language. Another string which is not in the language is 0110. As you can see, this string does not contain a hash sign and therefore it's not in the language. Another string that is not in the language is a hash sign followed by 0. As you can see, in this case we can read this string as the empty string hash sign followed by 0, and the empty string is not equal to 0. Therefore, this string is not in the language. Another example of a string not in the language is just 1 followed by the hash sign. In this case, once again, 1 is not equal to the empty string. The next example of a string which is not in the language is 000 hash sign 000 hash sign. In this case, the string contains more than one hash sign and therefore it is not in the language. Similarly, 0 hash sign 0 hash sign 0 is not in the language because it contains more than one hash sign. Similarly, the empty string is not in the language because it contains no hash sign. So for a string in the language B, it must consist of a string of zeros and ones, followed by the hash sign, followed by the same string. Those are all the strings that are in this language B. What we want to do now is to design a Turing machine M such that M accepts exactly these strings. So M should accept all the strings in B and it should reject all the strings that are not in B. What we want to do is design a Turing machine that can actually compare two strings over zeros and ones. That's the core problem here. So in order to define our Turing machine, we must have some intuitive idea about how this Turing machine would work. Let us first try to describe this Turing machine informally. This machine will work as follows. In the first pass, the machine will make sure that the input is of the form W1 followed by a hash sign followed by W2, where W1 and W2 are strings over zeros and ones. So in this phase, the machine will make sure that there's only one hash sign in the whole string that has been given to it, and all the other characters are zeros and ones. Then the machine will repeatedly scan the input and match each character of W1 with one character of W2. That is the intuitive description of this Turing machine. The first phase of this Turing machine will make sure that the input consists of only one hash symbol and all the other symbols in the input either zeros or ones. So there is a hash sign and there are some zeros and ones before the hash sign and some zeros and ones after the hash sign. This means we have our two strings. The second pass will actually make sure that everything that comes before the hash sign matches with everything that comes after the hash sign. And this would be done by matching the characters of the first string with the second string one symbol at a time. This is the intuitive description or an informal description of this Turing machine. Let us now define this Turing machine formally. Formally, our Turing machine will have 14 plus 2, 16 states. It will have states Q1 up to Q14, accept state and a reject state. Well, what is the input alphabet? The input alphabet in this case is 0, 1 and the hash sign. These are the input symbols that can be given to this Turing machine. The work alphabet in this case will consist of the symbol 0, 1, hash sign, a special symbol which will be used to cross out characters, which is written as X here, and the blank symbol. Of course, Q1 is the start state, QA is the accept state, and QR is the reject state. Delta, the transition function, which is the most important part of a Turing machine, is given by the following state diagram. If you look at this state diagram, you would find that it's slightly different than the state diagrams that we have seen before. This state diagram does not have the state QR or the reject state in it. What does that mean? Well, in this state diagram, we're using the convention that all the arrows which are not specified go to the reject state. So, for example, if you're in a state and you see a symbol and you realize that that state and that symbol does not have an arrow coming out with that label, that means the machine should go into the reject state. Let's look at this state diagram in more detail. If you see the state diagram, you realize that the machine consists of two parts. So there are two branches of this machine. From the state Q1, if the machine sees a 0, it goes into one side, and if it sees a 1, it goes to the other side. In this case, the machine is simply remembering that it saw a 0 or a 1. From the state Q2, how can the machine reach the state Q6? Well, as you notice, the machine is skipping over zeros and ones, moving right. When it sees a hash sign, it goes into state Q4, and then once again skips over zeros and ones, moving right. And then when it sees a blank, it reaches the state Q6. So the machine will reach the state Q6 only when it has established the fact that the input consists of zeros and ones, followed by a single hash sign, followed by some number of zeros and ones. From then on, the machine starts looking for a 0 in the second string. So in the state Q8, the machine skips over all zeros and ones moving right till it finds a hash sign, and now it knows that it's scanning the second string in its input. So the input is W1 hash sign W2, and it's going over W2. It skips all the cross symbols, and when it sees a 0, it crosses it off. Q12 is once again a rewind state. This is when the tape head moves all the way to the first cell of the tape. When it finds the first cell, Q13 starts moving right, and then the first 0 that it sees, it goes back into Q8, because in the second string it will match this 0. On the other hand, if it sees a 1, it goes back into the state Q9 because it would have to match a 1. Let us now look at what this Turing machine will do if it were given a specific input. Let's look at the behavior of this Turing machine on the input 011 hash 011. As you can see, the first phase of this machine will convert this input into blank 11 hash sign 011. It'll just change the first symbol to a blank, thereby marking the left end of the input. Now the machine starts looking for a 0 in the second string. When it finds a 0, it crosses it and starts all over again. So from this configuration, if the tape contents are blank 11 hash symbol 011, the machine will cross off the first 0. Next, it goes over the input and finds a 1, and so it starts looking for a 1 in the second string. Now it crosses off the 1 and is looking for a 1 in the second string. The tape contents are going to be a blank, followed by a cross, followed by a 1, followed by a hash symbol, followed by a cross. And it would be looking for a 1 in the second string. So the machine would be looking for a 1 after the hash symbol. It finds a 1 after the hash and it also crosses it. Now it goes back and similarly matches the last one in order to finally reach the following tape contents. Blank followed by 2 X's, followed by a hash symbol, followed by 3 X's. The next time this Turing machine goes over this tape, it realizes that all things have been matched, so it accepts the input. Let us look at an animation that we have made of the working of this Turing machine. As you can see in this animation, the Turing machine is going over and over its tape. It's trying to match one symbol of the first string with one symbol of the second string. Whenever it's successful in matching, those symbols are crossed out and the machine starts over again, thereby matching the next symbol of the first string with the next symbol of the second string. In case all of the symbols are successfully matched, the machine goes into the accept state. We want to look at another example. Let us design one more Turing machine before we go on. Let's look at the language C, which is defined as follows. The language C consists of all strings A to the I, B to the J, C to the K, where K is I times J. We also want I, J, and K to be greater than or equal to 1. So the language consists of A's followed by B's, followed by C's, and it should have the property that if I take the number of A's and multiply them with the number of B's that I found on the string, that should equal the number of C's in the string. So once again, the language consists of a consecutive block of A's and a consecutive block of B's followed by a consecutive block of C's. The length of this string has the following property. If I take the number of A's in the string and multiply it with the number of B's in the string, I get the number of C's in the string. Let us look at some examples of strings that are in this language. For example, the string ABC is in the language because all A's are in the beginning, then we have B's, and then we have C's, and there's 1A, 1B, and 1C, and 1 times 1 is equal to 1. So this string happens to be in the language. Another string in the language is AA, BB, CC, CC. Because it has 2 B's and 2 A's, 2 times 2 is 4, so the string must have 4 C's, which it does, and therefore this string is in the language. The string AA, A, BB, CC, CC, CC is also in the language, once again because 3 times 2 is 6. There are 3 A's, 2 B's, and 6 C's in this string. We should also look at some examples of strings that are not in this language. Let's have a look. Some strings that are not in the language are AB. In this case, there are 0 C's, and they should have been 1 C because we saw 1 A and 1 B. 1 times 1 is 1, so we were expecting 1 C. For the same reason, AABB is not in the language. AABB, CCC is not in the language because we have 2 B's and 2 A's, and 2 times 2 is 4, so we were expecting 4 C's, but there were only 3, so this string is not in the language. Similarly, the string BA is not in the language because our language consists of strings in which all A's come in the beginning and B's follow, and which are followed by some number of C's, and this string is not of that form. Similarly, the string CAB is not in the language because C's come before A's. Let's now try to define a Turing machine that accepts this language C. Our plan is, first we will try to define this Turing machine informally. Once we have an informal description of this Turing machine, we can convert that informal description into a more detailed description. In this case, what I'm going to do is give you an informal description of this Turing machine, and then it would be your homework to convert that informal description into a formal and precise description. Let us look at how we will solve this problem informally or intuitively. We will first scan the input and make sure that the string on the input tape is of the form A star, B star, C star. If it is not of this form, we will simply reject this input. This would make sure that the string is of the correct form, and now we only have to check the number of A's, B's, and C's. The second pass, what we will do is we'll cross off an A and scan to the right till we find a B. Now we will shuttle between the B's and C's, crossing one B and one C till all the B's have been crossed out. If you run out of C, you will simply reject this input. This phase is going to be repeated till all the A's are crossed off. So if all the A's have not been crossed off, what we are going to do is continue. If all the A's have been crossed off, we'll check if all the C's have been also crossed off, and in this case accept. Well, what will happen if there are some A's left? What we will do is we'll restore all of the B's and repeat this process over again. Why would this work? So the basic idea is cross off an A and then go and for each B cross off a C. Once this is done, come back and see if there are any more A's. If there are more A's, restore all the B's and repeat this process. So why would this process work? Let's check what this Turing machine does on a specific input, or what this informal description will do to a particular input. Let's say that the input is AA, BB, B, followed by 6 C's. We will first check if the string is of the form A star, B star, C, and it is, so we will continue. So the tape contents after we have done this checking will look like X prime, A, B, 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 followed by 6 C's. Since there are 3 B's, we'll shuttle between B's and C, crossing them off. So we will cross off all the B's and we will cross off all the C's. In this case, we will get the following tape contents at the end of this phase. There'll be X prime followed by A, followed by X, X, X double prime, followed by X, 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 and C, C, C. See, the marker X double prime shows where the B's would have ended. In this case, we find there's still one A left, so we will restore all the B's to get X prime A, B, 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 X, 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 C, C, C. Now we cross off another A to get X, X, 3 B's, 3 X's and C's. Now we will shuttle between B's and C's, crossing them off, and in the end we'll get X prime, X, 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 X double prime, followed by 6 X's. In the next pass, we'll realize there are no A's left and no C's left, so we will accept this input. What I have given you is an informal or an intuitive description of this Turing machine which accepts this language C. I have not done it formally. It is your job, it is your homework to define this Turing machine precisely by giving a formal description. Remember, in order to formally describe a Turing machine, you must tell me 7 things. You must tell me what the input alphabet is, which is easy in this case. You should tell me what the work alphabet is. You should tell me what the set of states is. You should tell me what the start state is, what the accept state is, what the reject state is, and finally and most importantly, you must tell me what the transition function is. In order for you to give me the transition function, you can either tell me the transition table of this transition function, or if you want, you can describe the transition function via a transition diagram. Let me give you a hint about solving this problem. You would have noticed that I used the symbol X prime in order to mark off the first A. This symbol can also help the Turing machine remember what the leftmost cell of the Turing machine is. Similarly, if you want, you can use different symbols to cross off B's and C's. This way, you would know where B's were and where C's were even after you have crossed them out. Use this idea and come up with a formal description of a Turing machine using a state diagram which accepts this language C. Let us now look at one more example. Once again, we will not solve this example in detail, but only give an informal description of the Turing machine that would accept this language. Let us look at another example given in the book. Let's look at the language E. E consists of all strings of the form #, x1, #x2, all the way up to #xl, where each of these xi's is a string over zeros and ones. And all these xi's are distinct. So if I is not equal to j, then xi cannot equal to xj. This problem is also called element distinctness. You are given L elements, x1 up to xl, separated by #, and your job is to make sure that all these elements are different from each other. So each element that occurs there is distinct from the other ones. Here is a high-level description of the Turing machine M4 that accepts this language E. Let's say that the input is W. What we will do is put a mark on top of the leftmost tape symbol, and if that tape symbol doesn't happen to be a #, we will simply reject the input. Now what we will do is we'll scan to the right of the # and find another # and put a mark on top of it. If no hash is encountered, then we'll simply accept the input. Now what we will do is we will zigzag over the two strings that are to the right of the marked #. And if they happen to be equal, we will reject. We will move the rightmost of the two marked hash symbols to the next one. No next hash symbol is encountered, then we'll move the leftmost one to the next one. If no such hash symbol is available, all the strings are compared, so we will accept. Then we will repeat this process over and over again. Once again, we'll zigzag and make sure that the two strings are not equal and continue to step 4 and so on and so forth. Let us look at what this Turing machine will do on a particular input. Suppose the input is a # followed by a 0, followed by a # followed by 0, 1, followed by a # followed by a 0, 0, 0. As you can see, in this case, all the strings between the # are different, so we should accept this input. So we will start by marking the first #. This means the first string has to be compared with all the other strings. So the first string 0 is being compared with the string 1, 0. Since they are not equal, now the first string 0 is being compared with the string 1, 1. As you can see, the rightmost marked hash symbol is moving to the right each time. Now the string 0 will be compared with 1, 1. Since they are not equal, then we'll compare the string 0 with the string 0, 0, 0. Since they are not equal, we will try to move the rightmost marked hash sign further to the right, but we don't find any hash sign there. So the left one has to move one step forward, which means now the string 1, 0 is being compared with the string 1, 1. This process will continue till 1, 0 is compared with all the strings, and then 1, 1 is compared with all the strings, and after comparing them we haven't found any matches, so we are done. There is a very simple algorithm or idea behind the workings of this Turing machine. Suppose if you give me L strings and I want to know if all of them are distinct, what I can do is take the first string and compare it with the second, third, fourth, fifth, all the way up to the Lth string and see if it matches with any of them. If it doesn't, then I'm done with the first string. So now I can take the second string and compare it with the third, fourth, fifth, all the way up to the Lth string. If I find a match, then I have found a match and I can reject the input. On the other hand, if I don't find a match, I'm done with the second string and now I can go to the third one and try to compare it with the remaining ones. The formal description of this algorithm can be given as follows. Let L be the number of strings on the tape, for I going from 1, 2, 3 up to L, and for J going from I plus 1 up to L. Compare the string xi and xj. If they are equal, reject. Otherwise, if the Turing machine successfully goes through, or the algorithm successfully goes through all these loops, we can accept the input, as we have established that all strings are distinct from each other. From now on, we will not look at transition diagrams, or we will not describe Turing machines in great detail. What we will do is usually give an informal description of the Turing machine. It would be up to you to convince yourself that all the informal descriptions of Turing machines that we are giving can actually be converted into formal ones. That you can take the informal descriptions and convert them into exact definition of Turing machines, which will do exactly what we are saying the informal description does. This is a bit like programming. For example, in your programming classes, your teachers often give you a vague or an informal description of an algorithm, and then your job is to go home and code these informal algorithms into programs. The programs are precise and they follow a certain syntax. Similarly, what I will be doing is describing informally some Turing machines to you. It would be your job to convince yourself that you can actually give formal descriptions of these Turing machines. Most Turing machines that do anything useful contain hundreds, if not thousands of states. It's very difficult and messy to describe these Turing machines formally. If I give you a state diagram which consists of hundreds or thousands of states, the state diagram hardly conveys any intuition about how the Turing machine works. However, an informal description conveys a lot more. It conveys the intuition, the basic algorithm or the principles on which the Turing machine is operating and therefore doing a specific task. It is going to be much more fruitful for us to look at informal descriptions of Turing machine rather than formally specifying all the Turing machines. Let us now think a little more about what other kind of Turing machines we can have. Can we have some variations in these Turing machines and add more power to it? So the next topic we are going to discuss is variants of Turing machines. Can I do something to a Turing machine? Can I add some more components to a Turing machine that will make it more powerful? Well, it would turn out that the answer to this question is no. Nevertheless, we must convince ourselves of this. One variant of Turing machines is a K-tape Turing machines. Now suppose we take our basic model of a Turing machine, which only has a one tape on which we write the input, and the Turing machine uses that tape to do its work also. What if a Turing machine were to say have more than one tapes? Let's say a Turing machine has 2 tapes or 5 tapes or 500 tapes or 50 tapes. Will that make a difference? Will that make our model more powerful? Let's formally define a K-tape Turing machine. What is a K-tape Turing machine? Well, a K-tape Turing machine formally is going to be once again a 7-tuple. The first component of this Turing machine is going to be Q, the set of states. The second thing is going to be the input alphabet, which we will once again denote with sigma. The work alphabet, which is gamma. Q0 is going to be the start state. QA is going to be the accept state. And QR is going to be the reject state. However, the transition function is going to be very different now. Because this Turing machine reads K symbols at the same time, because it has K tapes and K heads, each head is placed on one of the tapes, it will read K symbols at the same time. So the Turing machine will have to decide how to replace all the symbols that it's scanning, and it will have to make a decision for each head whether the head moves left or right. We are not going to restrict the tape heads to be moving all in the same direction. Each head is allowed to move independently on its tape. Therefore, the transition function will look like follows. The transition function is going to map the set Q cross gamma to the K to the set Q cross gamma to the K cross L, R to the K. Let us look at what this transition function is doing. It looks at the current state, then it looks at all the symbols, the K symbols that are currently being scanned by each head. It decides to go into a new state, and for each symbol it decides what to replace that symbol with. Therefore, it's mapping Q cross gamma to the K to Q cross gamma to the K, meaning it's telling what are the replacements for all the symbols it has read. Furthermore, the component L, R to the K tells each head whether to move left or right. So a K-tape Turing machine is quite complicated. There are K heads, the Turing machine is in a state, and then it decides by looking at all the contents of the K heads or all the current symbols that the K heads are scanning, it decides to do something. It decides what the new state is going to be. It decides what the first head is going to do, meaning what it will replace the symbol with and whether it will move left or right. It also decides that for the second head and the third head and so on and so forth for all K heads. It seems when we look at a K-tape Turing machine, let's say a 50-tape Turing machine, it seems that it's much more powerful than a single-tape Turing machine. However, we will show this is not the case. Another variant of a Turing machine is what is called a multi-head Turing machine. This kind of Turing machine only has one read-write tape. However, instead of just having one head, this Turing machine has several heads which scan the input. So for example, the Turing machine may have 2, 3 or 5 heads. In general, the Turing machine will have K heads. All these heads will move independently. We can formally once again define this Turing machine by saying that it's another 7-tuple where Q is the set of states, sigma is the input alphabet, gamma is the work alphabet, and Q0 is the initial state, QA as usual is the accept state, QR is the reject state. Once again, the delta function will be different from a single head Turing machine. The delta function will map Q cross gamma to the K to Q cross gamma to the K cross LR to the K. This means if the Turing machine is in a particular state, it would look at all the symbols that it's reading and decide how to replace these symbols, and it would decide which head moves left and which head moves right. Another very interesting model of Turing machine is a Turing machine with a two-dimensional tape. This very interesting Turing machine was studied in Alan Turing's original paper. A Turing machine with a two-dimensional tape can be thought of as a Turing machine that is working, instead of on a tape, it's working on a piece of paper. The Turing machine reads the piece of paper, it reads the current symbol, and depending on what the current symbol is, it decides to replace the symbol, and then its tape head can move left, right, up, or down. So formally, we can define a Turing machine with a two-dimensional tape as follows. Once again, it would be a 7-tuple consisting of Q, the set of states. There'll be an initial state, accept state, and a reject state. Furthermore, sigma is going to be the input alphabet and gamma is going to be the work alphabet. However, in this case, the transition function is going to map from Q cross gamma to Q cross gamma cross L, R, U, and D. L, R, U, and D represent the 4 natural directions that you can follow when you are working on a two-dimensional piece of paper. You can either move up, down, left, or right. We will show in the next lecture that all these models of computation are not more powerful than a one-dimensional Turing machine which works with a single tape. All these models are not more powerful than the original model that we have worked with. This is very important in computer science. All the variants of Turing machines that we are going to study, we will show that they are equivalent to the original model that we have studied. What does this mean? Suppose you make a Turing machine that accepts some language L, and suppose you make a Turing machine which uses 50 tapes. What I can do is I can make a single tape Turing machine which accepts the same language. Therefore, by increasing the number of tapes in a Turing machine does not increase the power of the model that you are working with. Similarly, suppose you make a Turing machine that uses a two-dimensional tape. Well, I can make a Turing machine which only uses a one-dimensional tape and a single head and perform exactly the same task. That is, it will accept the same language as the one that was being accepted by a two-dimensional Turing machine. Roughly, this is what the Church-Turing thesis is. Remember, we had said that Turing machine is the ultimate model of computation in the sense that no one has ever thought of a reasonable model of computation that is more powerful than Turing machines. By showing that k-tape Turing machines are equivalent to a one-tape Turing machine, and by showing that k-head Turing machines are equivalent to a one-tape Turing machine with one head, and by showing that a two-dimensional tape, a Turing machine which works with a two-dimensional tape, is equivalent to a one-tape Turing machine, we will give evidence that it is not possible to improve the power of Turing machines by simply adding more heads or adding more complicated tapes or two-dimensional tapes or three-dimensional tapes and so on. This would be very strong evidence of the Church-Turing thesis. However, this would not be a proof. As I had said before, the Church-Turing thesis is a thesis. It is not a theorem. Therefore, there is no way one can prove the Church-Turing thesis. I would invite you to try to come up with a model of computation that you think is more powerful than a Turing machine. If you do so, do send us an email because that would be an exciting development. However, I myself do not believe that there is any model of computation which will have more power than that of a Turing machine. Let us think a little bit about why a two-tape Turing machine is not more powerful than a one-tape Turing machine and how we may convince ourselves of that. Well, suppose you design a two-tape Turing machine which accepts some language. So you have this two-tape Turing machine that performs some computation. What I can do is I can start thinking about what a configuration of a two-tape Turing machine would look like. Remember the concept of a configuration for one-tape Turing machine? What we did was we specified what was the contents of the tape and what was the state of the machine and which symbol was being read currently by the tape head. So if you give me a two-tape Turing machine, I can describe its configuration by first telling you what is the state the Turing machine is in. Secondly, I can tell you what are the contents of the first tape and where the first head is placed. Furthermore, I will have to tell you what are the contents of the second tape and where the second head is currently scanning the input. However, what I can do is I can write down a configuration of a two-tape Turing machine linearly. What I can do is first write down the state of the Turing machine, then I write down a special symbol, then write down what are the contents of the first tape of the Turing machine, and the symbol that is being currently scanned by the first head, well, I can put a special marker on top of it. Then I can write the contents of the second tape of the Turing machine, once again putting a special marker on the symbol that is being currently scanned. Since I have been able to write a configuration of a two-tape Turing machine linearly, what I can do is I can put it on one tape. So what I can do is design a one-tape Turing machine that simulates the behavior of a two-tape Turing machine. In the next lecture, we will formally prove that k-tape Turing machines are equivalent to one-tape Turing machines. After that, we will look at some other variants of Turing machines and prove that they are equivalent to a one-tape Turing machine. I will see you in the next lecture. Thank you and goodbye.